All right, so we're going to go over an example where we need to find the value of constant k such that this limit will exist. And the first thing I think we should notice is that we are trying to evaluate a limit where our input is approaching negative infinity. And that's actually where I'm going to start this to help me kind of wrap my head around it for a second. So if x is going to be negative, right, x has to be approaching a negative infinity. So we know for sure that x values are always going to be negative. So what that means is this exponent here and that value of x there are going to be negative. So I'm going to rewrite with the negative exponents right away. So for instance, if we're plugging in a negative x value to there, that's really going to look more like 1 over e to the 2x because the exponent becomes a negative. Same thing on the bottom here. When we replace that x value with some input that gets more and more and more negative, it's going to look like 1 over e to the kx plus 3. Now, since I already rewrote the negative exponent, when I rewrite this limit symbol, I'm going to write this as x going to positive infinity because I've already accounted for the negative when I rewrote the exponent. And that's just kind of fancy notation per se. But it's important to keep track of that. If I put in negative infinity, I would have gotten to this back and forth argument where I'd keep flipping it and keep flipping it. So by flipping it once, I don't need the x value to go to negative infinity over more. Now this looks kind of like, well, when I see something like 1 over e to the 2x, I know that a limit as x goes to infinity of that one would be 0. So this part here, that's good for me because I can evaluate that part of the limit. The one thing we're kind of trying to figure out though is what's happening with this. But that looks really, really, really similar. So if I had 1 over e to the kx, when would that tend to 0? Well, it would tend to 0 if this big exponent stays on the bottom. In other words, the exponent's going to stay on the bottom if it remains positive. Right? It needs to remain there. So the value of k can't be negative then. Right? So if k was positive, we'd have this thing 1 over e to the kx. Pick any number bigger than 0. And eventually, as x gets huge, this is also going to tend to 0. So if k is greater than 0, we know that the limit will now look like this. It'd be 0 minus 5. And then this term here would tend to 0 because, again, k is a positive exponent. If it helps you to be something tangible, think of something like 1 over e to the 3x or 1 over e to the 10x or 1 over e to the 1000x. As long as k is a positive number, that exponent on e is just going to stay there and get huge. So it'll also tend to 0 plus 3. So we have one instance where we know the limit exists. So let's think about some other cases though. Now, what I was doing, I'm going to recopy how I handle the negative exponent. So we had something like 1 over e to the 2x minus 5, and then 1 over e to the kx plus 3. And then we were taking the limit as x got super huge. Now, we already talked about k being positive. Let's think about if k was negative. Well, if k was negative, then this term with 1 over e to the kx, the exponent here would be a negative number again. So it would flip back over to look like e to the kx. So let's think about that. So if k was a negative number, we would rewrite this one more time as the limit as x is going to infinity. Now on top, we still have the same expression. And on the bottom, now this, because this negative k value times that positive x value would give us a negative exponent, this whole thing here is going to go back up on top of that fraction. So I'm going to rewrite that as e to the kx plus 3. Well, it's a little bit different here, but I can still use some properties of limit. So I'm going to evaluate the limit on the numerator first, which is easy to do. That limit is going to be 0 minus 5, which is negative 5. And then on the bottom, I'm going to evaluate the limit of the denominator separately. Now with this one, what we notice as x is going to get super huge, the denominator is just going to approach this giantly, infinitely huge number. Now I can't actually perform division by infinity, but negative 5 divided by an absolutely huge number is going to be 0. So this limit also will approach 0 if k is a negative number, and that limit exists. So we should probably check what happens at 0 then. Because right now we almost have all real numbers where it works. We've highlighted everything that's negative, we've highlighted everything that's positive. Let's check what happens right here at 0. So if we plugged in k was actually equal to 0, we can rewrite one more time. And I'm going to actually go back to, well, let's just rewrite. So we would still have that limit as x is going to infinity. And I'm already taking care of that negative exponent again. But if k was equal to 0, this would be 1 over e to the 0 power, which I'm going to erase right away because e to the 0 power, or anything to the 0 power, is just going to be 1, and 1 over 1, I'm just going to replace right away as 1. So on the bottom we get plus 3. So we can evaluate this limit, right? This term is going to go to 0, minus 5 plus 1 over 3. So it gives us negative 5 over 4. And that means that that limit exists too. So we've shown that this limit exists for all real numbers. So k can be anything. K belongs to any number of the real numbers. You don't have to use that fancy notation, but k can be any real number. I do think it's important to also look at a graph of that function. So in Desmos here, what I've done is I've just loaded in the function f of x in the upper left-hand corner. I've just put in a slider for k because I don't know what that value would be. And for this slider, you can set the range of that slider to be whatever you want. Just for simplicity, I'm going to do negative 100 to positive 100. I know we just went over all real numbers, but I think this is fine for now. So what we're looking at here is we're trying to determine the limit when x is approaching negative infinity. So we're looking at the end behavior of the graph over here. So we're really going to focus on this, what appears to be a horizontal asymptote on the left here. What I want you to do is watch the asymptote on the left as I change the slider of k. Now the value of the asymptote might change, but that's not the question. The question is we just want it to exist. We want that limit to be there. So as I start to slide this, we can see really, like for a lot of these values here, it doesn't really seem to change the limit. I mean, obviously it is, it's just that my scale is a little bit hard to see, but I can see when I'm sliding the value of k really large, it doesn't seem to be affecting the existence of a limit. It's clearly still there. Now over here, what we can see is it changes, right? That horizontal asymptote clearly changes value when k is negative, but it still exists, and then I continue to get more and more negative. So you can see no matter where I put this slider, there's still a horizontal asymptote to the left. So we know that the limit will exist for all values of k.